Welcome back for the lecture on Dynamics of Fluid 2 or Fluid Dynamics Part 2. So in our earlier lecture of Fluid Dynamics, we have covered the Euler's equation of motion, Bernoullis equation and the numericals based on the Bernoullis equation. In this lecture, we are going to give focus maximally on the applications of Bernoullis theorem. Then one of the favorite application of Bernoullis theorem, Venturi meter, Orifice meter, Pitot tube, then hydraulic coefficients of an orifice and numericals based on Venturi meter and hydraulic coefficients. So this we are going to cover in this unit. So already I had explained in the content the practical applications of Bernoullis theorem. So Bernoullis theorem is having so many applications. Bernoullis theorem is very important to solve the fluid flow problems, and important applications of Bernoullis theorem, that is practical application, is nothing but one is Venturi meter, Orifice meter and Pitot tube. Now one by one we will discuss. So Venturi meter, Orifice meter are the devices which are used to measure the rate of flow of a flowing fluid through a pipe or a closed conduit. So therefore Venturi meter, Orifice meter are used to determine the rate of flow. This Venturi meter is designed or developed by scientist Venturi, G.B. Venturi. Hence the name is given as Venturi meter. So this Venturi meter is consisting of three parts. One is in convergent cone, convergent section. One is throat and another is divergent section. So this one convergent section, two is throat, and afterwards it is divergent section. So divergent section is always having more length than the convergent section, and convergent is having less length, because in convergent section fluid is accelerating, in divergent section fluid is retarding. If you carry acceleration within small length, no problem, but to have the retardation and to have the flow flow should be attached with the surface. For that, the retardation should be carried out for a bigger length or for a greater length. Therefore, divergent section is always having more length and than the convergent section. Now, let us consider, as the Venturi meter is used for calculating the discharge of the flowing fluid through the pipe. Therefore, we have to derive the expression or equation for calculating the discharge through the Venturi meter. And for that, we are going to apply the Bernoullis theorem. Let us consider one Venturi meter. Okay. Now D1 is the diameter of the inlet. Okay, of the Venturi meter at inlet. Then section H is the pressure head difference between the two sections. This is inlet section and another is throat section. It is called a throat section, constant area, or it is also called as constant area section, where area is constant. But from in a convergent, area goes on decreasing towards throat, and divergent area goes on increasing. In convergent, area decreases, convergent area goes on increasing. Now let us consider these two sections. Let us consider P1 upon rho g is the pressure head at section 1. V1 is the velocity of the fluid at section 1, or okay, inlet section, and Z1 is the datum potential energy at section 1. And similarly, P2 upon rho g, V2 square upon 2g, and Z2 are the pressure, kinetic head and potential head at section 2, that is throat section. Let us apply the Bernoullis theorem for that, and we consider that ideal theorem. Therefore, no energy loss we are going to consider. Therefore, P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2. But as the both section 1 and section 2 are at the same height from the datum, or for horizontal cases, Z1 is always equal to Z2. Therefore, the Z1 and Z2 will get cancelled, and therefore, what in the Bernoullis theorem for section 1 and section 2 if you apply, it will become what? P1 upon rho g plus V1 square upon 2g is equal to P2 upon rho g plus V2 square upon 2g. This implies P1 minus P2 upon rho g is equal to V2 square minus V1 square divided by 2g. But this P1 upon P2 upon rho g is nothing but what? If you connect one differential manometer here differential manometer, then H, it P1 upon rho g and P2 upon rho g, the pressure head difference is nothing but H, and that we can get with the help of here manometer, pressure differential manometer. And therefore P1 upon P2 is the difference, and it is given by H. Therefore, we put the value H is equal to V2 square minus V1 square divided by 2g. But continuity equation we know up at section 1 and 2. A1 V1 is equal to A2 V2. Therefore, V1 we have to write in terms of V2. That is A2 upon A1 into V2. If you put the value of V1 in terms of V2, okay, therefore we'll get the value H is equal to V2 square upon 2G minus A2 V2 divided by A1 bracket square divided by 2G. And if you go for that, V2 square upon 2G will take common and it will become 1 minus A2 square divided by A1 square. And the simplification, V2 square divided by 2G into A1 square minus A2 square divided by A1 square. This is going to be H. Therefore, put the value of H in this equation. Therefore, V2 square upon 2J is equal to 2GH into A1 square divided by A1 square minus A2 square. And therefore, V2 is equal to the square root, become simplified, A1 divided by square root of A1 square minus A2 square into square root of 2GH. But we know that discharge is equal to Q is equal to either A1 V1 or A2 V2. But we know value of V2, therefore Q is equal to A2 V2. This represent Q is equal to A2 into A1. If you put the value of this, or we can A1 A2, finally A1 A2 divided by square root of A1 square minus A2 square into square root of 2G. And this is called as theoretical discharge formula through the Venturi meter. This formula is called as A1 A2 divided by A1 square minus A2 square into under root of 2G is the formula to calculate the discharge through the Venturi meter, theoretical discharge. But always actual discharge is different than theoretical discharge. Therefore, Q actual is can be calculated by multiplying this theoretical discharge by one coefficient. That coefficient is called as coefficient of discharge, and this is called as CD is equal to, or CD is nothing but ratio of actual discharge to theoretical discharge. Therefore, Q actual is equal to CD into Q theoretical, and Q theoretical we know. Therefore, Q actual is equal to CD into CD into A1 A2 divided by A1 square minus A2 square into square root of 2GH. And CD is the coefficient of discharge. Always it is less than 1, and for Venturi meter it is nearly equal to 1, and its value is 0.92. Okay, now this is going to be the Venturi meter formula we know. Now we will see the numerical on Venturi meter. Then a horizontal Venturi meter with inlet and throat diameters they have given 30 centimeter and 15 centimeter respectively. Then is used to measure the flow of water. The reading of differential manometer is to be given as inlet and throat is 20 centimeter of mercury. So H is given as X 20 centimeter of mercury, and determine the rate of flow. Take CD is equal to 0.98. Okay, now the formula we know here, that is CD Q is equal to CD A1 A2 divided by square root of A1 square minus A2 square into root 2GH. So in this equation we have given, we know CD A1 A2 we can calculate, H and H we have to calculate. And for this, therefore here A1 we can calculate by the diameter 30 centimeter is 0.3 meter. It will become 706.85 centimeter square. Let us will consider in centimeter square. Then D2 is 0.15 centimeter. Area will become 176.7 centimeter square. A1 we got CD 0.98. Now how X difference in the two section pressure head is given in terms of mercury. Then there is one formula, that is if the manometric fluid is heavier than the flowing fluid. So manometric fluid is mercury, which is heavier than the flowing fluid in pipe is water, and there we have to use the formula H is equal to, that is conversion of X into H. So X is manometric head with respect to mercury, but we want with respect to flowing fluid, that is water, and that formula is H is equal to X into bracket SH upon SO minus 1, where SH is specific gravity of heavier fluid, that is mercury, it is we know 13.6, and SO specific gravity of water is 1. If you put in that case, it will become 12.6 into X, and therefore it will become 20 into 12.6, that is 20 is the pressure difference with respect mercury X into 12.6, it will become 252 centimeter of water. And if you substitute all values here, we will get the answer, that is 125. Afterwards in here 125,756 centimeter cube per second. But always discharge we have to express in terms of liter per second, and therefore it should be divided by 1000, and it will become 125.756 liter per second. So this is the numerical for us how to solve the numerical on Venturi meter. Then another important device that is based on the Bernoullis theorem is the Orifice plate or Orifice meter. So Venturi meter is very difficult to manufacture. It having little bit complicated shape, and when accuracy is not required, we can go for Orifice meter. So this is a device is there, rate of flow again cheaper than Venturi meter, works on the same principle of Venturi meter. Only here Orifice plate we have to keep in the pipe so that to get the obstruction or to get the pressure rate difference. The orifice diameter is kept generally 0.5 of the diameter of pipe, and differential manometer is connected for section inlet and that orifice section, and we get the pressure rate difference. And similarly like this, here it is the orifice plate is there. Now diagrammatically is a orifice meter is orifice plate or orifice meter orifice plate, and here we can say there is a manometer is connected at inlet section and orifice section where the flow is gradually decreasing. That section is nothing but it is contracting section or orifice plate section. We have to put the pressure head difference end of the manometer, and we'll get the pressure head difference between 0.1 and 0.2. First of all, we'll get in terms of mercury. After, we have to convert into with respect to flowing fluid by the formula H is equal to X into bracket SH upon SO minus 1. So similarly, this is derivation a little bit complicated, but we can apply our instrumental derivation. Only 2.62 we have to replace by VO, where O represent the orifice section. Okay, so PO upon rho G is the pressure head at orifice section. VO square upon 2G kinetic head at orifice section. ZO is equal to potential head at orifice section. If we go for similar derivation, again this derivation or similar derivation like that Venturi meter, then we will get finally same formula like that of the Venturi meter, and that formula is there that here discharge, theoretical discharge to the Venturi meter is given, orifice meter is given by CD A1 AO divided by square root of A1 square minus AO square into square root of 2GH. Now, where CD is coefficient of orifice, coefficient of discharge of orifice meter, and the value is always less than 1. And as losses are more for the orifice meter, therefore the CD value is nearly equal to 0.6 in case of the orifice meter, and it is less accurate than the Venturi meter. Then another formula, another device which is useful for the determination of velocity of the flow. Okay, that device is called as Pitot Tube, and this device Pitot Tube is discovered by the scientist Henry Pitot. Hence the name is given as Pitot Tube. So what is this Pitot Tube is there? So this is going to be the flow. So it is a L-shaped. This is a, here it is going to be L-shaped tube is there. It is going to be L-shaped tube is there, immersed in a fluid which is flowing. Okay, and let us consider the two section. One is at the exactly at the entrance of the Pitot tube. It is called as nose of the Pitot tube, and one section at the flow stream we can consider. So where the flow is having a pressure P1 upon rho G, velocity V1 square upon 2G. And at section 2, pressure will be P2 upon rho G plus V2 square upon 2G plus Z2. But and these two sections are at the same elevation, therefore Z1 is equal to Z2. And what we will consider that now when the water will enter into the nose of the Pitot tube, what will happen that as here with this water will flow with very high velocity, because this is in the streamline, velocity is very less because the area available for the flow is more and discharge is same only, therefore Q is equal to area into velocity, therefore area is more, therefore velocity is going to be less in at section 1. But when the fluid is entering, water is entering at section 2, therefore what will happen here, discharge is same, but as area decreases, velocity again increases, and this velocity increases suddenly, and due to that the pressure that head is going to be increasing, and that by H. So at point section 1 the head available pressure head is equal to capital H, but at section 2 the head will directly increase because of the increase in velocity. This is called as dynamic pressure head. So it is called as H, small h is called as dynamic pressure head, and is nothing but what, whatever the velocity is increasing at section 2, due to that is V2 square upon 2G is equal to small h, and this h if we calculate, then velocity at section 1 we can calculate. Okay, so this is going to be, this is right angle, the lower end is there. So theoretical velocity through the Venturi meter is given by v1 actual. V1 theoretical is equal to only square root of 2gh, where h is equal to, here whatever the, we are getting the rise of pressure due to velocity change, it is called as h. Therefore v1 velocity we want to calculate at section 1. Okay, and therefore v1 is equal to square, theoretically square root of 2gh, but actually it is cv into root 2gh, where cv is called as coefficient of Pitot Tube or coefficient of velocity, and this value is generally taken as 0.94. Okay, so this way, through the, by the use of the Pitot Tube, one can calculate the velocity of flow at any streamline. So if we can insert this particular Pitot Tube, or we can make this Pitot Tube up and down, and at any section, at any elevation, we can find out the velocity of flow through the in the pipe, and this is going to be what, velocity v is equal to v actual, or v cv into root 2j. Cv is coefficient of velocity or coefficient of Pitot Tube, and the value is 0.94 that we usually take. Now we'll consider the flow of fluid through the orifice. Okay, now let's consider one particular tank, a circular tank, and for this one circular orifice is fitted. Okay, let H be the head available for the orifice. So this potential head available for the orifice is equal to capital H. Okay, now this flow will go through the velocity in the form of jet. So when this water will emerge in the form of jet through the orifice, and this is going to be jet. Okay, circular jet. So this is divergent cone is going to form. Afterward, the jet will become convergent. But at one section, the area of that jet will become less, and that point is called as vena contracta. So vena contracta is the at section of that jet where the area of cross section becomes very minimum or minimum. That is called as what, vena contracta. Okay, now this vena contracta will consider as a section 2, and we want to calculate how much the velocity of the water or velocity of fluid flowing through this orifice. That velocity we want to calculate, and for that again this is also, this entire system is going to be application of Bernoullis theorem. Therefore we apply Bernoullis theorem at section 1, where section 1 represent the inside this particular reservoir, and here orifice section, vena contract section will consider as a section 2. If you apply it, Bernoullis theorem, P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2, plus Z1 is equal to Z2, as these two sections are at same height, same elevation. Therefore Z1 is equal to Z2. Okay, now here what we have to consider that, therefore P1 upon rho g plus V2 square up V1 square upon 2g is equal to P2 upon rho g plus V2 square upon 2g. Now P1 upon rho g is equal to H. P2 upon rho g is atmospheric pressure head, and is 0, and therefore H plus 0 is equal to V2 square upon 2g. Therefore V2, the velocity of theoretical velocity through the orifice is V2, is given by equation square root of 2gh. Okay, so this is going to theoretical velocity through the orifice, and discharge, theoretical discharge through orifice is equal to, if this theoretical velocity multiplied by area of cross section, that is called as AO. Okay, now depending on this particular diagram, we have to define the three hydraulic coefficients of an orifice, and these are going to be coefficient of velocity, coefficient of contraction, and coefficient of discharge. So we'll go one by one. The coefficient of velocity, it is the ratio of actual velocity of jet at vena contracta to the theoretical velocity through the orifice, and as already we have derived the theoretical velocity through the orifice is equal to, given by equation root 2gh. Okay, therefore here this CV will represent is equal to what, V velocity at vena contracta, and root 2j is theoretical velocity. So this CV is equal to square V divided by square root of 2gh. That ratio is called as coefficient of velocity, and the value for this is taken as generally 0.595 to 0.99, but generally the value is taken as 0.98 for sharp edged orifices. Then we'll go for coefficient of discharge. The coefficient of discharge is already defined as, it is nothing but what, here actual discharge, ratio of actual discharge flowing through the orifice to the theoretical discharge, actual discharge to the theoretical discharge. So therefore Q divided by Q theoretical. And one more coefficient is there. It is called as coefficient of contraction, in short CC, and defined as the ratio of here area of jet at vena contracta to the area of orifice. So area of jet at vena contracta is less. Therefore CC AC divided by A. Therefore this should be also always less than 1, and generally it is taken as 0.69. So area of jet at vena contracta is minimum. Area of orifice we can calculate by formula pi by 4 do square. So AC upon A represent the coefficient of contraction, and this value is generally taken as point in between 0.61 to 0.69, and generally average value is taken as 0.64. Now there is relationship between the CD, CV and CC. So what is that? CD is equal to actual discharge to theoretical discharge. So actual discharge is nothing but what? Actual velocity. Q is equal to area into velocity. Actual velocity into actual area divided by theoretical velocity to theoretical area. But actual velocity to theoretical velocity is called as coefficient of velocity, and actual area to theoretical area is called as coefficient of contraction. Therefore CD is equal to CV into CC. So this relation is very important. Coefficient of discharge is always equal to CV into CC, and the value of CD to be taken as 0.61 to 0.65, and general purpose 0.62, because losses of more in case of the orifice meter. Now one problem we will see on this particular hydraulic coefficients of an orifice. Then the head of water over an orifice of diameter 40 mm is 10 meter. So capital H is given as 10 meter. It is not centimeter, it is a printing mistake. It is 10 meter. And diameter of orifice is 40 mm means 0.04 meter. Find the actual discharge and actual velocity of jet at vena contracta. CD is equal to 0.6 and CV is equal to 0.98. Therefore, what they have given? Diameter, from the diameter we can calculate area by 0.01256 meter square, because pi by 4 d square. Okay, then CD is given as 0.6, CV is 0.98. Then CD is equal to actual discharge, CD divided by Q, CD divided by theoretical discharge. Therefore, what theoretical discharge? V theoretical into area of orifice. Therefore, it is given as area of orifice we know into root 2 GH theoretical velocity. It is given by 14 meter per second, because if you put 2 into 9.81 into 10, theoretical velocity is 14 meter per second. Theoretical discharge will become 14 into area of orifice 0.01758 meter square per meter cube per second. So it is printing mistake. Therefore actual discharge will coming as 0.6. It should multiply by CD. 0.6 into theoretical discharge. Therefore actual discharge is 0.6 into 0.01758, or is equal to 0.01054 meter. Or if you consider in liter per second, it will become multiply by 1000, so it will become 10.54 liter per second. Then CV is equal to again 0.98, actual ratio of actual velocity to theoretical velocity, but actual velocity is equal to 0.98 into theoretical velocity, and actual velocity is coming as what? 13.72, because theoretical velocity is 14 meter per second, and CV is equal to actual divided by theoretical velocity. So this way we have to solve the numericals on this hydraulic coefficients of an orifice. These numericals are asking in the examination for 4 marks. Numericals on the Venturi meter may be asked for 5 to 6 marks. And there is no numerical treatment in the syllabus mentioned, that is for Orifice meter, Pitot Tube. So they may ask the numericals on Bernoullis Theorem, Venturi meter and hydraulic coefficients of an orifice. Out of these 3 variety, one variety will be definitely there in the examination. So you are requested to study this chapter very in sincere manner, so that you will get good marks in section 1. Thank you very much and best wishes for your study.